Let's explore page replacement algorithms. This is how operating systems manage memory. We'll cover first in, first out or FIFO optimal, also known as Belady's algorithm, and least recently used or LRU. Why do we need page replacement algorithms? The first reason is physical memory is limited, especially when compared to virtual memory. Page faults occur when the pages that we need aren't present in the physical memory. Efficient replacement strategies play a key role in reducing the number of page faults. The main goal here is to reduce memory access time and also maximize throughput. Now let's understand the FIFO page replacement algorithm. FIFO stands for first in, first out. It replaces the oldest page present in the memory. It maintains a queue of pages based on their arrival time. FIFO is pretty simple to implement and easy to understand. But it doesn't consider the page usage frequency. Also, it suffers from Belady's anomaly. Let's look at an example. Here is a reference string consisting of pages 1, 3, 0, 3, 5, 6, and 3. And we have 3 frames. Initially, frame 1 gets page 1 and there is a page fault. Then frame 2 gets page 3 and there is a page fault. Next, frame 3 gets page 0 and there is a page fault. The next reference is page 3, which is already there in frame 2. So there is no page fault. Now the next reference asks for page 5, which results in a page fault. So page 1 in frame 1 gets replaced by page 5. Next reference asks for page 6, which results in a page fault. So page 3 in frame 2 gets replaced by page 6. Finally, the next reference asks for page 3, which results in a page fault. So page 0 in frame 3 gets replaced by page 3. Here's a look at a function called FIFO page replacement, written in JavaScript, that takes pages and frame count as input. It initializes frames as an empty array and page faults as an empty array. A for loop iterates through the pages array. Inside the loop, it checks if the page is already present in the frames. If the page is not present, which means a page fault occurred, then the page index is pushed into the page faults array. It checks if the frames array has reached its maximum frame count. If so, it removes the oldest page by calling the shift method on the frames array. Finally, the current page is pushed into the frames array. Now let's visualize a FIFO queue. The queue contains the pages 1, 3, and 0. In the visualization, we can see that, when a page fault occurs, we check if the frames are full. If the frames are full, we remove the page at the front of the queue, which is the oldest page. Then the new page is added to the rear of the queue. The page at the front will be the next victim for replacement. Time complexity of the FIFO algorithm is order of n, where n is the number of page references. And space complexity is order of f, where f is the number of frames. Now let's discuss the optimal page replacement algorithm, also known as Belady's algorithm. It replaces the page that will not be used for the longest period of time in the future. It requires future knowledge of page references. It provides the lowest possible page fault rate and is used as a theoretical benchmark. However, it is not implementable in real systems since it requires future knowledge. Let's look at an example. Here we have a reference string consisting of pages 7, 0, 1, 2, 0, 3, and 0. And we have 3 frames. Initially, page 7 comes in and there is a page fault. Then page 0 comes in and there is a page fault. Next, page 1 comes in and there is a page fault. The next reference asks for page 2, which results in a page fault. Now we need to replace a page. When looking ahead, 7 is not used again, while 0 and 1 will be used. So we replace 7 with 2. The next reference is page 0, which is already present. So there is no page fault. The next reference is page 3, which results in a page fault. Between 0, 1, and 2, page 1 is not used. So page 1 gets replaced with 3. The next reference is 0, which is already present in the frames. So there is no page fault. Note that at position 3 we need to replace a page. Looking ahead, 7 is not used again, while 0 and 1 will be used. So we replace 7. Here's a function named optimal page replacement, written in JavaScript, that takes pages and frame count as input. It initializes frames as an empty array and page faults as an empty array. A for loop iterates through the pages array. Inside the loop, it checks if the page is already present in the frames. If the page is not present, which means a page fault occurred, then the page index is pushed into the page faults array. It checks if the frames array has reached its maximum frame count. If so, it calls another function named replaceOptimalPage to find the optimal page to replace and replace the page. Finally, the current page is pushed into the frames array. To make an optimal decision, we identify when each page in memory will be used next. Then we replace the page that won't be used for the longest time. If a page won't be used again, it's the optimal choice. Note that this requires future knowledge of the reference string. Let's discuss the LRU page replacement algorithm. LRU stands for least recently used. It replaces the page that has not been used for the longest time. It is based on the principle of locality of reference. It requires tracking when each page was last accessed. It provides better performance than FIFO in most cases. It approximates the optimal algorithm using past history. Let's look at an example. Here is a reference string consisting of pages 2, 3, 1, 0, 3, 2, and 4. And we have 3 frames. Initially, page 2 comes in and there is a page fault. Then page 3 comes in and there is a page fault. Next, page 1 comes in and there is a page fault. Then the next reference asks for page 0, which results in a page fault. Now, between pages 2, 3, and 1, the least recently used page is page 2. So page 2 is replaced with 0. The next reference is page 3, which is already present in the frames. So there is no page fault. The next reference is page 2, which results in a page fault. Now, between pages 0, 3, and 1, the least recently used page is page 1. So page 1 is replaced with 2. The next reference is page 4, which results in a page fault. Now, between pages 0, 3, and 2, the least recently used page is page 3. So page 3 is replaced with page 4. Here is a JavaScript function called LRU page replacement that takes pages and frame count as input. It initializes frames as an empty array, page faults as an empty array, and last used as an empty object, which will be used to track last usage time of each page. A for loop iterates through the pages array. Inside the loop, last used object is updated with the current page index. Next, it checks if the page is already present in the frames. If the page is not present, which means a page fault occurred, then the page index is pushed into the page faults array. It checks if the frames array has reached its maximum frame count. If so, it calls another function named replaceLRUPage to find the least recently used page to replace and replace the page. Finally, the current page is pushed into the frames array. We can visualize the LRU data structure, which consists of the pages 1, 0, 2, and 3. Note that the least recently used is on the left and the most recently used is on the right. To implement LRU, we track when each page was last accessed. When a page is accessed, we move it to the most recently used position. When replacement is needed, we select the least recently used page. It can be implemented using a linked list for order of 1 operations, or using a counter or timestamp for each page access. Hardware implementations make use of special registers or bits. Let's compare the performance of the page replacement algorithms we discussed. FIFO has poor performance but is the simplest to implement. It can be used in basic systems. Optimal has the best performance but is impossible to implement. It serves as a theoretical benchmark. LRU has good performance with moderate complexity of implementation. It is used in most modern systems. There are other algorithms like clock and second chance which have good performance and are simple to implement. The page fault rate comparison chart shows that Optimal has the least page faults while FIFO has the most page faults. LRU and clock algorithms have fault rates between the two. To summarize, Page replacement is crucial for efficient virtual memory management. FIFO is simple but can suffer from Belady's anomaly. Optimal algorithm provides the theoretical minimum page faults. LRU offers a practical balance of performance and implementation complexity. Different algorithms are suitable for different system requirements. When implementing page replacement algorithms, there should be a balance between algorithm complexity and performance gains. Hardware support can significantly improve LRU implementation. Workload patterns heavily influence algorithm effectiveness. Modern systems often use hybrid or approximation algorithms. Proper frame allocation can be as important as the replacement strategy. Next, we will discuss advanced page replacement algorithms like clock, second chance, and working set. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.